Okay, so now exercise 4, we want to see the difference between the MLE and the MAP. So let's read the exercise. We have a coin, unknown probability theta. We flip it 10 times and we have 7 heads. So we have to write down the likelihood and compute the maximum likelihood of theta. So a bit of, let's construct a little toolbox here first. First, we want to know that if x follows a binomial distribution, which it does here, basically it's a repeated Bernoulli distribution with parameters n and theta. So n is the number of times you repeat the experiment. Theta is the probability of success, which in our case we will say is a probability of heads. So if x follows a binomial distribution, then the PDF of x, the probability that x equals a certain number of heads k will be equal to n choose k times theta to the power k times 1 minus theta to the power n minus k. This is a handy formula we will keep in mind now to solve this exercise. Another thing we want to know is Bayes' rule. Quick refresher on Bayes' rule. So Bayes says that the posterior, so the probability of theta given the data, is equal to the likelihood probability of the data given theta, the parameters, times probability of the parameters over the probability of the data. Now, it's good to know that this guy is called the posterior. This guy here is called the likelihood. Sorry, let me move this here. This guy is called the prior, and this guy is called the marginal. It has other names. I forgot what. Call it the marginal for now. And usually it's good to know the marginal is very intractable, hard to compute. So usually you use the proportionality sign, which you'll see later while doing MAP. But for now, okay. So they want us to write the likelihood, right? The probability of the data given theta, the parameters, which is exactly this guy, right? So we know that the data is distributed, given the description of the experiment here, according to a binomial distribution, right? So maybe I'm abusing notation here, but basically the data follows a binomial distribution with n equals 10, right? Because we flip 10 times, and the probability of heads theta, which is unknown, which hopefully we'll estimate now. We know that k is equal to 7, n minus k is then equal to 3. And so this all says that the probability of the data given theta is equal to n choose k, which is 10 choose 7, times theta to the power 7 times 1 minus theta to the power 3, right? This is the likelihood. Okay, now we want to compute the MLE of theta. So we want to maximize the likelihood. So we want to maximize this guy, right? So way of writing the estimate is theta hat. Hat is usually mathematics for we're estimating here. Theta hat MLE is equal to argmax theta of the likelihood, right? So probability of the data given theta. This, by the way, is a fancy way of writing D for data, if you don't get my handwriting. So that's great. We have a formula to find the maximum likelihood. You just have to maximize this guy here. Now, a good thing, a very computationally convenient thing to do when maximizing is to maximize over the log likelihood. So this is equal to argmax theta log of the likelihood, right? Why can we do this in very quick 2 seconds? This is the log function, like everyone knows, right? And what's important here is the fact that it's monotonic. So maximizing over a monotonic function is invariant, if you will. The maximum of this guy will be maximum of this guy because log is monotonic, so it's not going to change the maximum theta that we're going to get. And taking the log makes it very computationally convenient to solve these types of problems. Sometimes you will see people also do argmin over theta of the negative log likelihood, where this guy has a name, the negative log likelihood. But forget this for now. So we want to maximize the log likelihood, right? And to maximize the log likelihood, let's first of all write it down, right? Right, what we have to take basically now the log of this guy, right? So log of this guy is equal to, well, and I'm writing in detail here so that the steps are a bit clear. Feel free to skip ahead or speed up or whatever. So the log of, well, log of the likelihood is log of this, which is going to be equal to log 10 to 7 plus log theta to the power 7 plus log 1 minus theta to the power 3, right? Why is that? Because we use the rule here, log AB is equal to log A plus log B. Okay. We can further simplify here. This implies this is equal to log 10 to 7 plus 7 log theta plus 3 log 1 minus theta, right? And here we used another rule, which hopefully everyone knows. Here we used log an is equal to n log a, right? Okay, perfect. Now we have this. To maximize this, we want to take the derivative and set to 0. So we're going to take the partial derivative. Sorry, I'm lazy. Partial derivative with respect to theta of this. Well, this guy is going to go, right? Because it doesn't depend on theta, so its derivative is 0. This guy is going to be 7 over theta. And then this guy is going to be, right? So how do you write this again? It's going to be 7 over theta minus 3 over 1 minus theta. We want to set it equal to 0, right? So we write equals 0 here. And then we solve for theta. So this implies 7 over theta is equal to 3 over 1 minus theta. This implies 7 times 1 minus theta minus 3 theta equals 0. This implies 7 minus 7 theta minus 3 theta equals 0. This implies 7 equal to 10 theta, which gives us our final answer for theta MLE is equal to 7 over 10. Perfect. So that's our MLE estimate. some people would make the argument you have to further cement that this is a maximum, not a minimum. You have to take the second derivative and prove that it's positive or negative. In this course, I haven't seen us really go in this much detail. Usually just take derivative set to zero and then solve. So let's leave it at that now. And let's go to question 2.